So in this section, or this video, we're going to be looking at section 3.9, which has the title Related Rates. And so before we get too into it, I think maybe we'll just start with a straightforward example, just so you can kind of see what this is going to be about. And so I'm going to pause here while I write down the question, and then when I come back we'll take a look. Okay, so here's our example question. An oil rig springs a leak, and the oil spreads in a circular path around the rig. If the radius is increasing at a rate of 30 meters per hour, how fast is the area increasing, the area of the patch, when the patch has a radius of 100 meters? Okay, so how are we going to figure this one out? Well, we need the formula for the area of a circle, right? And so we know that just in general, right, that area is pi r squared. Okay, now what's happening in this problem is that the radius is increasing in time, right? And so r is a function of t. Okay, so instead of just writing r, then we're going to write r as r of t. And so similarly then, that means, whoops, sorry about that, that you see here that a must also be a function of t then, because r is a function of t. So a is also a function of t. Okay, so therefore I would rewrite my formula as a of t equals pi times r of t squared. Okay, and now let's read some of what else is happening here. The radius is increasing at a rate of 30 meters per hour. So let me color that in here. So how would I translate that information into mathematics? Well, that piece of information would be the rate of change is going to be the derivative, so that's dr over dt. And it sounds like this is constant, right? So the derivative is going to be constant at 30 meters per hour. So you could include the units here, 30 meters per hour. Good. And so what that suggests then is we're going to differentiate both sides of this equation. So dA over dt is equal to pi times, now for the derivative of this we're going to need the chain rule, right? Because this is a composition of two functions. So the outside function is going to be, the derivative is going to be 2 times whatever's in there to the 1 power. So our function is the inside function here, radius. And then we multiply by dr over dt, or just r prime. Good. And so how fast is the area increasing means figure out what dA over dt is when the patch has a radius of 100 meters. Okay, so I think we're now ready to plug everything in. The rate of change of the area is pi times 2 times the radius, which is going to be 100, times the rate of change of the radius is 30. Good. And so if we multiply that out, what do we get? 6,000. 6,000 times pi. And so the units here would be meters per hour as well. Good. And so the title of this section then is called Related Rates, because as you can see here, right, the rate of change of the area is related to the rate of change of the radius. Okay, and so you're going to find that this is typically the issue in all of these problems, is that the derivative of one quantity is going to depend on the derivative of another. And so that's what we're going to mean by related rates problems. Good. And so this is also typical where the problem will set up some some geometry that we can use. Okay, so we're going to need to be able to do a little bit of geometry here, some geometry. So geometry. What are some other geometric things we might be looking at in this section? Well, you might see things like areas of a triangle, right? A circle, a rectangle. All of these things we assume that you know, right? And then also perimeter of things, perimeter of a circle or a rectangle. That's also some things we assume you know. Also Pythagorean theorem, of course. Pythagorean theorem we should know. A couple of things that I wanted to mention especially is, I'll go ahead and come down here to a new section here. A couple things to keep in mind. Okay, so one thing to keep in mind is how to translate the statement A is proportional to B. So if I have two things that are proportional to each other, that means that you can write them as A equals K times B, where K is said to be the constant of proportionality. Okay, and so that's one way of translating an English sentence into a mathematical statement. Good. One other thing I wanted to, I guess I need to say one more thing. Some volumes of more, there are some formulas that I will give you. So formulas to be given are things like volume of a cone. I don't expect you to have that memorized. Although once you work with it for a while, you'll probably get it memorized just because. Volume and surface area of a sphere. I'll give you that. Okay, those kinds of formulas that you're probably not going to have memorized, I will give you. By the way, there is an insert at the beginning of Stewart, right? See the first page insert in Stewart. It's right before it's kind of a hard cardboard page that's right at the beginning of the book. I'm not sure if it shows up in the electronic copy or not. But anyway, it's kind of a cheat sheet kind of thing where it has lots of formulas on it. And so that's kind of handy to have. The last thing I wanted to mention is similar triangles. Something we've probably learned in the past, but maybe a little rusty on. So when you see similar triangles, that means you have two triangles with equal angles. And so let's see, this angle is equal to this angle, say, and this angle is equal to that angle, for example, and then that forces the last angle to be equal, right? Oops. So maybe 3 lines on that one. Okay, so then if this is triangle with ABC, and this is triangle with capital A, capital B, capital C, then similar triangles says that the ratio of little ab to big AB, the hypotenuse to hypotenuse, is the same as the ratio from the leg to the leg and the leg to the leg. So therefore we could say AB over AB is equal to BC is equal to AC to AC. So again, the way to think about it, right, is hypotenuse to hypotenuse is the same as, or small to big is small to big to small to big, yeah, each of the sides. And this is, by the way, this common number is called the scaling factor. Good. All right, so this formula will come in handy frequently in these problems, and in fact the way it's going to be presented typically is you'll see one triangle inside of another and they'll both be right triangles. Okay, so this is typically the sign for similar triangles. So if you see this kind of object here. Go for the similar triangles. Good. Okay, so I'll stop there and we'll just do several examples in the next video.